Hi, in this video I'm going to be talking about proportions, dealing with side lengths and area, surface area, volume, lots of good stuff here, relationships between shapes of different sizes as long as they're similar. Before we get going, let's talk about what scale factor is, okay? A very important feature that we're going to talk about is scale factor. And when I say scale factor, I mean how many times bigger or smaller is a shape. So for instance, I have two rectangles, if you can see that I have them drawn here, a 3 by 5 and a 9 by 15 rectangle. Okay, and there is a scale factor of 3 when I go from one rectangle to the next rectangle. In other words, what I'm saying is the scale factor is 3. That means that I've multiplied and I've made each of the side lengths, individual side lengths, 3 times as long. So 3 multiplied by 3 gives me 9. 5 multiplied by 3 gives me 15. Okay, and what I want to talk about is if we go through and we calculate the area of these two shapes, you might notice something. The question is this. This is the big question and probably the big misconception. If I triple the side lengths, did I triple the area? And that's the common answer is yes, I did triple the area. Okay? And what I want you to notice here is if I count the boxes, I have 3 by 5, that's 15 boxes in here. The area is 15. 15 times 3 is 45. So is the area of this thing 45 boxes? And you'll see right away that the answer, no, it's not. It's not. It's 135, actually. It's 135 boxes in there. How did I get that? I took 15 times 9. And what you might notice is this. If I broke it down and I actually redrew, remember those 5 by 3 rectangles that existed? I could actually place those inside there. And I noticed then, if I draw a bunch of 5 by 3 rectangles, that there are exactly 1, 2, 3, 4, 5, 6, 7, 8, 9 of them that fit inside. So that's interesting. If I have a scale factor of 3, then the area is 9 times bigger. 9 times bigger. An area of 135. And that kind of leads us to a conclusion then. See, if we went down, oh, you know what? No, we're not ready for the conclusion yet. Let's go through and let's draw a couple of more examples, okay? 3 times scale factor, 9 times bigger. Maybe a relationship there. How about this, okay? I want you to notice, now first of all, these are similar shapes, and that's very important, just like the rectangles are similar. I have same angles throughout. I have 90 degrees in the middle, and then notice also, not only the angle is the same, but the sides are proportional. See, 8 becomes a 24, 3 times as big. 3 becomes a 9, 3 times as big. So all the side lengths follow, or whatever lengths, follow the same proportion. Well, what is the area of the triangle to the left? I would say the area of this triangle is 1/2 of 24 times 9. And the area on this one is 1/2 base, which is 8, times the height, which is 3. And the question is, by making this shape 3 times as large to get to this shape, did I make the area 3 times as big? Valid question. The area on the left one is 108, and the area on the right one is only 12. 12 times 3 gives me 36, not 108. Interesting. In fact, if I take 108 on my calculator and I divide it by 12, I get 9 again. If I make the side lengths 3 times as big, the area is 9 times as big. So the ratio of the side lengths, if I wanted to put a ratio of side lengths from big to little, that would be a 9:3 or 3:1 ratio. Typically we write that as a fraction as 3:1. But the ratio of the areas was 108 to 12, which we would reduce then to a 9:1 ratio, which we typically write as a fraction. So the ratio of the side lengths is 3:1, the ratio of the areas is 9:1. The same relationship that we saw here, right? The relationships here would be a 1:3 ratio, and the area relationship would be a 15 to 135, or we would say 1:9 ratio. What about circles here? Let's see here. Then we're going to try to draw a conclusion. You got a sneak peek at it there. Okay? Now this one doesn't have side length, this one has a radius. So we'll go ahead and say the ratios of one radii to the next radii. It's radii, it's plural of radius. The radius on the left one is a 3, and the one on the right is a 2, so it's a 3 to 2 ratio of radii. We would probably write that as a fraction, 3 to 2 relationship. But if I calculated the area, knowing that it's pi r squared, the area of this thing on the left is a 9 pi, and the area on the right is a 4 pi. So it's not a 3 to 2 relationship, it's a 9 to 4 relationship. Notice, by the way, I could put 9 pi over 4 pi. Why don't we do that real quick? It's a 9 pi to 4 pi relationship, but you know what? The pi's, they go away. So it's really a 9 to 4 relationship. Well, how in the world are we doing this? How do we get from 3 over 1 to 9 over 1? What's the relationship between 3 and 9? 1 and 1. How about this? How did I go from a 3 to a 9 and a 2 to a 4? So it's not multiplying by 3 each time. It's not doubling each time. It looks like maybe the relationship is this. If I take 3 and I square it, I get 9. If I take 2 and I square it, I get 4. If I have similar shapes and there is a ratio of side lengths, if I can write the ratio of side lengths as m over n, whatever m and n stand for, maybe it's 3 over 2, their areas, the ratio of the areas can be found by squaring those relationships. So, example problem here. That's the big one to write down. One more time. Look at this. Ready? Scale factor of 3. 3 times as big, 9 times the area. If the scale factor is 4, 4 squared is 16, 16 times the area. If the scale factor is 10, then the area is going to be 10 squared, which is 100 times bigger. So we can use that to do a problem like this. We're going straight to the tough ones, by the way. I'll help you with the easy ones in class. Let's say you need 3 ounces of shredded cheese to cover a medium 12-inch diameter pizza. So here's your medium diameter, 12 inches. How much shredded cheese would you need to cover a large 16-inch diameter pizza? Well, here's what I know. That 3 ounces is going to cover a certain amount of area. If I find the area of that pizza, I find out how much an ounce will cover, and then I could transfer it over here. I could turn this into a long problem, in other words, but here's what I know. Ready? There is a 12 or a 16 to 12 relationship of big to small, right? So if I take 16 over 12, which reduces down to 4/3, there's a 4 to 3 relationship between big and small. So as far as the area goes then, if I have a 4/3 longer diameter, then if I take 4/3 and I square it, that gives me 16 over 9. That's how many more times the area is. 3 ounces would cover this, so if I take 3 and I multiply it by 16 over 9, I'm going to need about 5.33 ounces of cheese in order to cover that large pizza. Hopefully that makes sense. Okay, the big idea is knowing that proportion. If I want to go from side length to area, I square. I square the ratio, and that gets me my multiplier, my scale factor for area. If that makes sense, then you're ready to go on the second video, which is about surface area. Can we take this same idea and apply it to the area of a three-dimensional shape?